Welcome to The Explainer. Okay, today we're tackling something that is notoriously difficult in the NLP world. We are talking about dynamic political stance detection. Look, politics moves fast, right? Alliances shift, new figures pop up literally overnight, and opinions, well, they're almost always implied rather than stated outright. So the big question is, how do we get large language models to essentially read the room when that room is constantly changing? Well, we're going to be exploring a pretty groundbreaking unified framework called GRASP-ChoQ. Let's dive in. Here's our roadmap for today. First, the political stance problem. Second, the GRASP-ChoQ solution. Third, data and experimental setup. Fourth, results and reasoning. And finally, limitations and impact.
Section 1. The political stance problem.
To really understand the solution here, we first have to understand the blind spot. Why do large language models actually struggle with rapidly evolving political events? Well, the answer lies in how political opinions work out in the real world. They are heavily implied. We're talking sarcasm, hyperbole, inside references, you name it. And LLMs struggle with this because their training data is static. They have a hard cutoff date. When real-world alliances change overnight, and we all know politicians are famous for never changing their minds, right? A standard LLM just cannot keep up with the unwritten rules of that new landscape.
Now, you might be thinking, hey, why not just update the model? Well, retraining an LLM every single time a political event happens is incredibly expensive. It's computationally heavy, and honestly, it often causes catastrophic forgetting of older data. So what about standard retrieval-augmented generation? Good old RAG. Standard RAG grabs relevant text documents based on semantic similarity. Sure, but it completely misses the hidden multi-hop relationships that are absolutely crucial to understanding politics. It doesn't inherently understand that the enemy of my enemy is my friend. It's just looking at vector proximity.
Section 2. The GRASP-ChoQ solution.
Okay, so let's look at the complete GRASP-ChoQ pipeline. First, we gather external political knowledge from Wikipedia, process all of that into chunks, and, this is the absolutely crucial part, we map it into a structured knowledge graph in a Neo4j database. Then, when a new tweet comes in, the system extracts the entities, pulls the relevant political context right out of that graph, and feeds it into an LLM using a structured chain of questions. It's not just retrieving a block of text, it's retrieving logical relationships.
Let's actually break that complex architecture down into 4 clear steps, just to make it super digestible. Step 1. Collect your political facts and build a knowledge graph using Neo4j to store those entities and exactly how they relate to one another. Step 2. When an input tweet arrives, extract the key political entities from it. Step 3. Use those extracted entities to retrieve a specific subgraph. You want the exact web of political relationships relevant to that specific tweet. And finally, Step 4. Instead of making a direct prediction right then and there, the system uses chain of questions reasoning to evaluate that historical and structural context, making a final, highly informed stance prediction.
So what does a retrieved subgraph actually look like? Well, notice how it maps out both explicit and implicit alliances. It connects figures like Sheikh Hasina to the interim government with very clear directional edges, things like opposition or involved in. This right here provides the crucial structured context that language models naturally lack. It basically hands the model a dynamic cheat sheet of exactly who is aligned with whom in the current moment.
But here's the thing. Just having the knowledge isn't enough. The model actually needs to know how to use it. And that is exactly where chain of questions, or CHO, comes in. CHO enforces structured logic. Instead of forcing the model to make a single blind guess on some highly complex tweet, it forces the model to interrogate the graph data. It asks things like, who is being criticized? Or which government is currently in power? It actively breaks the problem down into manageable, logical steps before arriving at a conclusion.
Conceptually, it's actually really helpful to contrast these different approaches. Think about a zero-shot LLM. It's essentially making a blind guess based on outdated training data. Naive RAG tries to help out by handing the model a dictionary of related texts, but it completely lacks relational structure. GRASP-ChoQ, however, acts more like a lead investigator. It actively retrieves a connected, logical graph of who knows who, and then uses a structured notepad, the chain of questions, to reason through all that evidence.
Section 3. Data and experimental setup. To prove this framework actually works, the researchers needed a fast-moving, really complex political environment. So they created the BPDisc dataset, which centered around the highly dynamic 2024 Bangladesh protests. To establish a truly objective ground truth, They used a rigorous manual annotation process. They looked at explicit political cues found right in user bios, filtering a massive stream of noise down to roughly 2,800 highly reliable golden truth tweets.
The key entities captured in this dataset really reveal the core of the conflict. We're talking about the specific figures, parties, and locations deeply tied to the event. And just to ensure uniform analysis across all the different language models they tested, non-English tweets within the dataset were carefully translated to English, while strictly preserving all the proper nouns.
So, what did they test it against? The researchers evaluated this framework using some seriously state-of-the-art large language models to establish a strong baseline. The lineup included GPT-4, GPT-4o, Gemini 1.5 Pro, Mistral Large Latest, and DeepSeek R1. These models were evaluated on accuracy, precision, recall, and, crucially, their F1 score. That gives us a really balanced performance measure across these complex classification tasks.
Section 4. Results and Reasoning.
Okay, so the defining metric of this entire study is 40.6. That is the massive percentage jump in the F1 score that the DeepSeek R1 model achieved on the BPDisC dataset when it was equipped with GRASP-ChoQ compared to its zero-shot baseline. I mean, think about that. A 40.6-point improvement is absolutely staggering when you're evaluating complex NLP reasoning tasks.
And the data shows that GRASP-ChoQ didn't just help one specific model either. It universally elevated reasoning capabilities across the board. By providing that structured knowledge and literally forcing step-by-step logic, F1 scores skyrocketed past zero-shot, few-shot, and naive RAG setups for every single model they tested.
If we compare the zero-shot baseline to GRASP-ChoQ, it reveals this massive stabilization. Without the framework, models suffer a really steep drop-off in recall. They just struggle to consistently identify stances. But with GRASP-ChoQ, performance tightly clusters at a significantly higher tier. And the paper's ablation study confirmed this exactly. If you remove the knowledge graph, the model guesses blindly. If you remove ChoQ, it gets totally overwhelmed by the graph. They absolutely must work in tandem.
Take this real-world example of a tweet evaluating digital transformation. It shows exactly why the synergy works so well. The user complains, saying electronic transfers are terrible, terrible. Now, a zero-shot model sees those negative words and incorrectly assumes the user is against digital transformation. But the GRASP-ChoQ model looks closer. Through its guided questioning, it realizes the user relies entirely on their phone and hasn't actually touched physical cards in months. It recognizes the hyperbole. It correctly flags the stance as in favor of digital infrastructure, completely preventing the model from being tricked.
Section 5. Limitations and Impact.
Now, as with all cutting-edge research, there are definitely some limitations we need to talk about. Currently, this is a text-only approach. It lacks multimodal reasoning, meaning it cannot analyze political memes, images, or videos, which, let's face it, are a huge part of modern discourse. Second, the effectiveness is obviously bound by the limited scope of the knowledge graph you built. And finally, while it's miles better at handling nuance, extreme political sarcasm remains a notoriously difficult hurdle for AI to clear completely.
And that brings us to our core takeaway. The true novelty of this research isn't just inventing knowledge graphs or RAG, it's integrating knowledge graph retrieval directly with chain of questions reasoning into a single unified framework. It teaches the AI not just what to read, but how to think about those relationships. Unifying these systems might just be the ultimate key to decoding dynamic political AI. So what do you think? Are structured graphs the future of LLM reasoning? Thank you so much for joining me for this explainer. Keep questioning and keep learning.